Okay, greetings and good morning. As we've discussed yesterday, also, we will begin our sessions with doing the recap of all the machine learning and statistical tools, the process that we need to follow, and then we will move to the generative AI concepts. So, whenever we start with any data related aspects, right, data related problems, we need to look at the stages of analytics. This is basically where we begin. So entire problem statement that comes from the customer has to be categorized into one of these stages, and we have four stages. The first one is descriptive, and of course diagnostics. So whenever we have a problem statement where we basically try to summarize what happened in the past, then we try to apply these strategies, what happened and why something happened. This will look into the past. And your data analysts basically come into the picture here because they are the people who take the historical data, try to summarize that using some business intelligence tool. So this is what your data analysts do. Next, we look at the predictive analytics, which basically talks about using this knowledge of past, like what happened and why something is happening, the reasoning. We will try and use that knowledge or that pattern to try and estimate what may happen in future. What may happen. Here we are talking about future. And this is where your machine learning engineers come into the picture. We use statistical methods, or we started using statistical methods, which can be explained using this equation, y is equals to f of x equation, which tries to define the relation between the outcome, which is being caused by some factors. Those factors are represented as x. This is predictive analytics. Yep. Krishna, you had a question? Yeah. Then we have prescriptive analytics. This prescriptive analytics basically talks about the solution that we need to implement to control the future. So here, what should be done? Right? This is basically what we do here. And what should be done basically is a strategy that needs to come from domain experts or business owners. And this would be an experimentation that we do to control the future, control the outcome. Because we know what is the relation between input and output, right? This function basically is representing that relationship. So when we talk about a specific outcome which is caused by these bunch of factors, we also mathematically represent what is the impact of each individual factor on the target. Then we try to pass the inputs in such a way that we get desired output. In a mathematical sense, if I write a simple example, y is equals to, let's say, 2x1 plus 5x2 plus, let's say, 3x3, so on and so forth. Then if I have x1 as some value, then 2 times of that is what is the impact on y, right? 5 times of x2 is what you are going to get on y. So this is rate of change, right? So the impact of x1 on y is 2. The impact of x2 on y is 5, so on and so forth. So because I know how much x1 is impacting, x2 is impacting, x3 is impacting, so on and so forth, I would try and control these inputs, which is x1, x2, x3, so that we get desired output. Right? So this is your prescriptive analytics, and this basically is your domain experts work. Now, generally, what we say is in the right pre-COVID times, I should say, all these four things together were job of a data scientist. The data scientist is basically, or data science is basically a discipline like your regular science, which basically talks about different aspects to ensure we get a desired outcome. Right? Control and research and all those things are part of the data science job role. Right? And you can see that there are different business consultant would also be there, domain expert. Right? So there are different roles and responsibilities within a data scientist. He or she should be able to don all these things. Now, it all depends on what kind of requirement the customer has. Depending on that, we will go for the respective solution development. It may not always be that we have to do predictive solution development, right? So descriptive analytics requirements might also be there. And those are one of the major projects in data related scenarios where we say the BI engineers or Tableau or Power BI experts, they basically design the charts. So when data keeps coming in, they keep developing these charts, they templatize it. And when new data comes in, the BI tools will refresh and then show the new details as well. All right, so that is with respect to your stages. Next comes the process management methodology, and here we'll talk about CRISP MLQ. This is the gold standard that is used. Before COVID, we used to talk about CRISP DM. I think Sambit, when we were discussing, it was CRISP DM, isn't it? 2019, I'm pretty sure it was until COVID 2020, it was CRISP DM. Around that COVID times, the methodology is upgraded into CRISP MLQ. So slight variations are there in CRISP DM and CRISP MLQ. And this is the process management methodology, okay, or project management methodology. Okay, and this is also known as machine learning work flow or ML, machine learning development life cycle. This is the standard practice that we use. And it also contains 6 stages. Okay, this also contains 6 stages like CRISP DM, the previous one. The 6 phases are, the first one is business and data understanding. So business and data, they are very, very tightly coupled. That's why you see both of them merged together. Then the second one is data pre-processing or preparation. The third one is model building. Fourth one is model evaluation. Fifth one is deployment. These are the 6 stages, right? Sambit, if you remember, CRISP DM. Can you recollect?
Yeah, these processes. I mean, I can recollect. Yeah. But
Yes,
crisp.
the first one was actually split into 2. Business understanding was separate step, data understanding was separate step. So you had 6 stages in CRISP DM. But in CRISP MLQ, you can see they are merged together, data and business. Because business ultimately generates data, and if your data can be analyzed, business can also be understood, right? So they're very, very tightly coupled. But what is the added phase here is the 6th step. In CRISP MLQ, there's the 6th step is the improvement from CRISP DM methodology. And this basically talks about monitoring and maintenance. Monitoring and maintenance. This is basically after sales support that we discussed. Right? Over weekend sessions, we were talking about this. Right? So these are the 6 phases that we have in CRISP MLQ. Business and data understanding, of course, we need to gather all the requirements. We need to understand what data we are dealing with. Then we need to understand where the data is residing. Then we have to get the data. After getting the data, again, we have to do statistical analysis to understand what is the meaning of that data, right? It is all part of business and data understanding. We'll discuss in detail when right in the weekend sessions. But now, what we are talking about here is gather the information about business requirements. Okay, so I'll write very high level here. So the first stage is gathering business requirements, understanding the business and gather all the business requirements. Okay, we have to be very specific to the task that we need to solve, because in a business there will be a lot of problems and we cannot just divert into, right, delineate or and we should not be diverting into different problems. We need to delineate the problem and only focus on one problem at a hand, at our hand. Then we need to try and understand what is the data that business is generating. Data that business is generating. But this is not uh, the ultimate data that we will be using, because data might be generated in different scenarios by different processes, different touch points would be there, right? All the data may not be relevant to the problem statement that we are trying to solve. So we will have to try understand all the data that business is generating and identify the relevant data fields. Okay, we need to identify what are the relevant data fields. Then identify the source of the data points, or these data fields that we have identified. Then we do data ingestion. Data ingestion, what is the meaning of data ingestion, anyone? Yeah, what could be the meaning of data ingestion?
I mean, sometime we are missing some information, so we need to put inside the dataset something like that.
No. Ingesting means what? Taking, right?
Yes.
So data ingestion in other terminologies, you can say it is data collection. See,
Okay.
we have identified what is the data that is getting generated by the business. Then we have identified what is relevant data fields. Now we are also trying to see where the data is residing in the business. Where is that actual data sitting? Okay, the sources could be primary and secondary. Once we identify where the data is actually sitting, we have to get that data so that we can start processing, right? So into your processing environment, you're getting the data. That's called as data ingestion. Once the data is obtained, next we do preliminary statistical analysis. What is it also called as? Yeah, Samir, you should be able to tell me.
EDA, right?
Exactly. Preliminary statistical analysis is nothing but EDA. EDA means exploratory or elementary data
Analysis.
analysis. Okay, EDA is exploratory or elementary data analysis. This basically gives us a lot of meaning out of the data points that we have collected. And here we take univariate analysis. We start with univariate analysis. That means one variable. Uni means what? One variable. We'll also try and look at bivariate analysis. That means we'll take two variables together and try to understand what kind of relationship they have, how they are influencing each other, or how this pair is influencing the other variables in the data, right? All these things will be analyzed in bivariate. Then we will have multivariate, which is nothing but trivariate or 4, 5, right? Multivariate analysis. This way we go in phases wise in understanding our data. All right. So this is part of your business and data analysis. And post this, once we have understood the data in a better way, mapping that to the business context, mapping it to the business problem statement that we are trying to resolve, we will have to try and see what kind of misalignments or what kind of anomalies or what kind of challenges the data is having. All right, because data has certain standards that needs to be maintained, and we need to try and compare the data with respect to that standards. Why I'm talking about this is because ultimately you will have to use mathematical or statistical computations, right? You'll have to do mathematical or statistical computing on the data, right? Some mathematical equations have to be performed. Now, in order to perform this, the data should be in a specific format which will allow our computers to process. Now, if you remember over the weekend sessions, we were talking about data structures, primitive structure, non-primitive structure, etc. Right? And the ideal form of data in computers is a two-dimensional representation, which is nothing but your table. Okay, this is nothing but a table matrix. In mathematical terminologies, that is nothing but matrix. In data processing and right arranging the data in a table format in Python, basically is the standard way, and in Python we call it as data frame. In databases we call it as table, right? This is the most ideal or standard way to represent our meaningful data. And once the data comes into this form, your computers, along with your softwares that we basically deal with, right, gets the capability to process that data. And if you want to apply some mathematical computations, your table form or data form will allow the right application of wide variety of mathematical or statistical computations on that. So in short, this is the default representation. So we need to bring our data into this form, irrespective of what kind of data we are dealing with, whether it is on a business operational data, right? It could be in different sources, like CSV files could be there, text files could be there, application forms could be there, website RSS feeds could be there, or we might have API calls. It could be images, right? Whatever data it is, ultimately it has to come to a table representation so that it opens up the softwares like Python programming, which we use to process that data easily, right? So this refinement that I'm talking about is part of the next stage, which is data preparation stage or data pre-processing stage. Okay, data pre-processing or data preparation. It's like in any manufacturing sector. Okay, if you imagine any manufacturing sector, like we work for a steel manufacturing company, we are doing projects there. So what happens in that steel manufacturing right company is they procure raw ore. We call that right iron ore. So they purchase that in metric tons. Then they also have scrap material purchased by right purchased from different other companies, etc. And what they do is they melt all that steel. Now the scrap should be melted at different right temperatures. The iron ore that we are right procuring, that needs to be processed in a different manner. But ultimately, what they are doing is they're bringing everything together, removing impurities by whatever the process that they have to deal with, respective to the input that they are processing, right? And they combine all that refined material, which is the molten iron, right? The molten lava type, the liquid form of iron. Then they put that into molds, which will create the steel pipes. And then, of course, cooling process will be there. So there is a process, right, to achieve the end result. Same way, data may come from different sources, right? Now, all these sources basically are nothing but different softwares, right? As I was talking about, this could be a database, this could be a API call website, right? This could be an IIoT device, this could be a form, right? So on and so forth. There could be different sources. We need to understand how or what format the data is stored in, how these softwares are managing that data. And once we understand that, we try to transform that into a specific format. Here we are extracting, we are transforming the data into a specific standard format and then store that in a specific location. We'll load it. So here you will have refined data, right? Processed data. Now, what happens is the end users, who's data analysts or your management, reporting teams, machine learning engineers, AI engineers, all these people basically take the refined data for processing. What you're seeing here is called as ETL pipelines. Okay, this is how your data is acquired. So we are focusing on data pre-processing here in the transformation stage. Now, there are different layers to the transformation concept. What we are talking about in CRISP MLQ methodology, which is part of machine learning pipeline, is to deal with impurities in the data which is already in a table format, or while we are converting the data into table format, there could be some impurities or some gaps. What are those gaps? The gaps could be missing data. Some fields might be missing. Some might be exceptional cases. Those are outliers, right? So refine the data to get the data arranged in a two-dimensional table structure. Okay. Table structure so that it can be readily used for processing. So we are calling it as pre-processing stage because we are we're making this data for processing purpose, making this data ready for processing purpose, right? Refinement stage. And what challenges we can foresee? We may have duplicates. We may have exceptional values. What are exceptional values? What do we call them? Remember outliers? Do you guys remember outliers?
Yes.
What is an outlier?
The value or expected, things it doesn't suit under the limit of, what I can say, within the bounded limit. The value it may go either beyond that or kind of,
Hmm.
yeah.
So, in short, you can use this definition, right? Outlier is an exceptional value in the entire field, right? There could be one or more outliers, exceptional values, extreme values when compared to the rest of the data points. Now, handling outliers is very, very important because it influences the entire meaning of the data, right? So we may have these kind of exceptional cases. Missing values could be there, right? We may have mismatch of scale, that is nothing but magnitude, right? We may have data in non-numeric format. We cannot use them in mathematical computation. So we will have to convert non-numeric data to numeric data. Non-numeric values could be there. these needs to be converted to numeric values. We basically do something called as encoding, right? So on and so forth. There are many such challenges. These are some of the standard default problems that we will have, which needs to be addressed. Okay, here we do outlier treatment. Missing values, we do something called as imputation, right? There's one more thing called as typecasting, which needs to be done. So on and so forth. That there are basically a lot of right, these solutions that are given depending on what challenge the data is facing. We have to implement these pre-processing steps. These steps, right? These steps basically are added into a pipeline, machine learning pipeline steps. Okay, this is because whatever analysis that we are doing, right? The machine learning problem that we are going to develop, I mean, solution for machine learning problem that we are going to develop, right? Will always be developed using historical data. And when we talk about historical data, it will not be your entire data, it will only be a sample data, right? But what are we trying to do is trying to leverage the available data and then try to model this particular data, right? We're saying model. Now, this model will basically be implemented for the entire data. So sample data is representing this population. And we will use this representative data to model the relation between those fields. And we are trying to generalize this model and say this is kind of a pattern that we will have in business fields. Yeah, this is what we do. And if you remember, we talked about inferential statistics. We generally talk about inferential statistics. Okay. People who already have studied, I'm just trying to revise this terminologies. Inferential statistics is nothing but the result that we get on sample data. Okay, so the result that we get on sample data are called as sample statistics. Okay, for example, I want to analyze and understand the performance of, let's say, one B school, business school, like the likes of IIMs, IITs, right? And then we talk about ISBs. So a lot of MBA programs, right? Business schools, if talk about business schools, we talk about MBA. So a lot of universities are there, and we try to compare the performance of those universities. And then based on that, we rank them, isn't it? So when we are trying to analyze the performance of one specific university, like ISB, for example, which is the top-notch university, I'm taking this as an example, and compare this with any of other B schools. Okay. Now, what we do is we look at the students' data, outgoing students' data from this particular university or any other university that we want to compare. Okay, this is one university we have like this, multiple university. We'll take the alumni data, right? Already graduated or post-graduated, right, students. Now, do you think we will get entire list of all the students who have completed the education in this particular universities? No, right? We'll always get a, a sample because whatever is data available, that is what we take. We cannot try and achieve a feat where we say, no, nothing do we want to have every data. Okay, it's not possible. So we will take students' data, which will be a representative data. Okay, which is nothing but a representative data for the university. And then what we do is we will gather statistical evidences from these group of students and then try to represent that statistics for the entire university. Any analysis happens this way only, isn't it? So this process that we are going to implement is basically yielding statistics for us. And those statistics are used to infer or generalize meaning for population. That is the entire business scope. Okay. So this is basically the process that we follow. We call it as inferential statistics. So what we do is we basically try and take the data, historical data, do EDA, right? Understand the statistical information from that particular data. We will also understand what challenges the data has. So we do pre-processing. After pre-processing is done, we get clean data. We get clean data. This clean data will be used for model building. This next step, model building. Okay. Now, we work with historical data here, right? That means the past. But we are performing this entire development so that this development can help us predict values, right? We're basically doing for prediction purpose. Prediction purpose means I will have new data, right? New input. This new data should be passed through the ML model that we are developing here. And this should be able to give us the predicted results. Okay, predicted results. Using these predicted results, the decision will be taken. Appropriate decision would be taken. But when we talk about new data will be in the same schema, right? Same format of your historical data. Right? What is a schema? What do you mean by schema? Do you understand the terminology, schema? No? No, everybody's silent. Okay. So I'm assuming that you guys don't know what is schema. All right. So schema is basically data definition. Schema is a terminology which comes from your SQL databases. If I talk about RDBMS, right, this is one of the SQL databases, right? SQL databases. You can talk about Oracle database, you can talk about MySQL, we can talk about Microsoft SQL Server, Postgres, etc. We have RDBMS softwares. So in the RDBMS softwares, we will have, right, tables. This is the symbol of database. And within this, we will have a table. But if you look at the process of managing data in databases, the first step would be creation of a table. We first have to create the table. Inside a database instance, we will have to create a table. When you're creating, you are going to define the entire structure, right? The outline of the table. So you say, okay, this is a table. I'll give a name to this, right? Table 1. And in this table, I will have columns. Column 1. But this column 1 can contain integer values. Comma separated, I have column 2. Column 2 can have varchar of size, so much size. Column 3, float, column 4, right? Like this, we will have different definition given for each column, right? So this is basically this data, the frame of the table that we are defining, right? The structure of the table that we are defining is called as table schema. Okay, so that means there is a proper format or arrangement that data has to be represented in. This is the standard definition for the business. Okay, schemas are always predefined, as I told. So this will be the standard definition for the data in the system. So your historical data is also coming from the centralized repository. So when we talk about new data will also be stored in the same format. That means new data will also be in the same schema. It maintains the same schema. But when we were dealing with new data, we observed some challenges and we did some pre-processing steps. That means the new data that is in the same format should also go through the same sequence of steps that we have implemented on the historical data. Only then it can come into this format, the clean data format, so that the model can be used. Model can use that particular data. So when we define this pipeline, we are not just doing machine learning model used here, whatever development has happened, right? We don't use just that. We also use data pre-processing pipelines. So in the pipeline, we define the sequence of steps which are implemented here as well. Okay, data pipelining, very, very important. Read more about data pipelines. Okay, so it's nothing but the sequence of steps that we implement to ensure the data goes through the same sequence of steps because data is coming from the same format and data has to go into the model in a specific format, right? So any new data also has to go through the same sequence of steps. All right. So this is about your data pre-processing related aspects. Data pipelines have to be maintained. And then we use model building. Now in model building, this is where your actual machine learning concepts come. So when we talk about model building, we basically look at two different broad steps here. Okay, model building is nothing but representing the pattern in a mathematical form. But here we have unsupervised and supervised learning. Predominantly, we talk about unsupervised and supervised. We also have something called as reinforcement learning. We also have transfer learning. We have various other things come up, semi-supervised, etc. But all began with semi-supervised and supervised learning. All right. So what I'll do is I will try and write like this. Semi-supervised data is data which is basically used when we have unlabeled data. Okay, we have unlabeled data. That basically means we will have only X. Okay, and we are trying to perform multivariate analysis. Define hidden pattern from the data set that we have. We try to define rules or patterns in the data. Okay, identify hidden pattern or rules. And there are different type of algorithms like clustering algorithm, association rules. The PCA is one more technique, right? We talk about recommendation. Of course, recommendation engine is not part of your unsupervised learning directly, but that is also used. Okay. Predominantly, we talk about grouping. Okay. When we talk about unsupervised learning, we don't have labeled data and we are trying to do multivariate analysis. But when we talk about supervised data, it is applied on labeled data. That means we have X and we have Y. X is also known as input or also known as predictors, but there are different bunch of names. Whereas Y is the target that we require, right? It is nothing but your output. It's also known as output or target. And when we talk about supervised learning, when we have labeled data, this is where we do right? When we talk about unlabeled data here, we are basically trying to do what? Description. So we say descriptive analytics is being performed. Descriptive analysis. Whereas for labeled data, because I have specific variable of interest, I will be able to use that knowledge for defining a relationship, mathematical model for defining the relation between X and Y. Okay, here we say inputs, right? So predictive analytics. But again, here in supervised learning, the output that we already know in the table, right, in the data set, when we look at it, we can see that data has numeric, I'll write like this, numeric and non-numeric values. Non-numeric is also known as categorical values. Now, if the output variable, this output variable, if it is numeric, then it is easy for me to develop a mathematical expression, right? As I was giving an example, right? Y is equals to 2x1 plus 5x3 plus 10x, sorry, this is x2, 10x3 plus maybe 8x4. Like this, if I have an equation, a simple equation that you can see, right? It is all pluses. So it's a linear equation that we are seeing. And if I have everything as numeric values, then I will be able to solve this and get a result, which is again a numeric value, right? So I'll be able to use statistical measures here, right? Methods here. So mathematical equations can be very, very easily applied. But if my output is non-numeric, then can I use this mathematical equation directly? No, right? So if this is students' data, okay, if this is students' data, and Y is marks that student is going to secure, which could be in the range of 0 to 100, right? Marks could be between 0 to 100. So I will be able to do mathematical equation like this in order to understand how many marks would you be able to secure, isn't it? I'll look into all the past exams that you have written, then try to define the pattern to understand, right, how many marks you might get if you write an exam now, depending on all these factors like your age, preparation time, gender, address, the subject, the IQ levels, the material that is available. All these influence marks. So I'm trying to define that relationship in a mathematical form. And when I solve this, I may get a result which is lying between 0 to 100. Because it's a numeric value, I'll be able to do it. But what if my requirement is not about calculating marks, but rather I want to see if the student will pass or fail the exam? That means we are looking at non-numeric case. Can I directly use a mathematical expression to get this answer? No, right? I cannot say 2 plus 5 is equals to pass. 2 plus 5 is 7. It is not pass, isn't it? So it does not make sense for us to use a direct mathematical equation to calculate a non-numeric value. You cannot get that, right? It's not possible. That is the reason why we will use some alternate methods to get this non-numeric result. That means the algorithms that we are using vary here, depending on what are the capabilities of those algorithms. Okay, so the algorithms or the techniques, I would say, which are defined in such a way that they return specific output, right? They return some value as output. Right? This is nothing but your output. So if your output is numeric, then what algorithms should we use? The algorithms which have capability to give numeric output, isn't it? These algorithms which have the capacity or capability to return a numeric value, they are called as regressors or regression techniques. Okay, these are called as regression models or regressors or regression techniques. But if the algorithms are having the capability to also give you an outcome which is non-numeric in nature, then these algorithms are called as classifiers or classification techniques. Okay. In regression techniques, we have different variations depending on what we are trying to achieve, right? The value that we want to calculate. And in non-numeric approach, we also call them as shallow methods, the classification techniques that we are using. They will be able to directly tell that, okay, given this information about a student, the student may pass the exam or fail the exam. That would be the output of that model. Okay. Now, do you remember any of these algorithms? Anyone? Any of the algorithms? In fact, you can talk about unsupervised learning or supervised learning. Give me some examples. Yeah, what are the example algorithms that you can think of in unsupervised learning? Sambit, Anil, answer guys.
Clustering.
Very good. Yes. Clustering is there. Yeah. Anything else? I already talked about it, right? Dimension reduction. We can talk about association rules. Yeah. So these are typically the examples. And when we talk about predictive analytics, what examples can you think of? In regression, what are the examples? All right. Linear regression,
Yeah, yeah, yeah. Logistic
logistic
regression.
regression, yeah, nonlinear polynomial regressions. Yeah, Krishna, very good. Right. So regressors basically, right? And when we talk about classification techniques, what can you think of here? These are very important. Forgot models. KNN, Naive decision trees, ensemble techniques, all these are classification models. Here we don't use y is equals to f of x, statistical direct math, statistical equations, but we use an alternate right techniques like distance based techniques or probability based techniques. Decision trees are rule based approaches, right? So these have capabilities to yield result which is non-numeric in nature. Okay, so these are different algorithms that we basically have in supervised and unsupervised model building scenario. Depending on what data we are dealing with, what problem we are trying to solve, we will use that appropriate technique. But whatever the algorithm that we are using, that algorithm also should be evaluated, right? We need to check whether the final model, which is representing the pattern in the data, is actually representing it in the more generalized manner, right? We need to evaluate that. So for all the algorithms that we use, we also have to think of some evaluation strategy, model evaluation strategy, right? And what we do for model evaluation, how do we approach? Anyone? Anil or Sambit? What do you remember? The model evaluation techniques. Data partitioning, remember? No? I give my standard example. I've been using the same example from ages. A very good example. Let's say I have 10 students. Okay. I am to train them.
Yeah, I got it. Train data and test data. Yeah.
Exactly. We need to train. I'll continue the example anyways. Okay. So I have 10 students and I have my objective is to train these 10 students so that they can get a job. The subject that we are trying to train is, let's say, data science, AML. Okay, AI, ML. So in order to train these 10 students, what I'll do is I will take the subject, which is nothing but data here. And this data is, let's assume, 100 questions with answers. So I'm basically giving you a question bank, you can say. Interview question bank. So using these 100 questions with answers, I'm trying to train you. That means I'll say, hey, this is the question. And in order to understand that question, this is the answer. So I'll explain the answer. Right? That means I'm trying to explain the subject. But how will I know whether you actually learned the subject or not? Because ultimately I'll have to send you to the job, right? Job interview. That means you'll have to face an interview here. Unless until you clear the interview, you'll not get a job. How will I know that you are capable to clear the interview? You're among these 10 students. How would I know? I need to do my one evaluation myself, right? Internally, I need to do an evaluation. So what I'll do? I'll conduct an exam. But remember, I have only 100 questions with answers. This is all the question bank that I have. This is all I have, which is representing the entire subject. Like I don't have new questions. I have only these questions. So when I conduct the exam, I will have to choose some of these questions only. Let's say I'll take 10 questions, right? But from the 100 question set. Now, what happens if I conduct an exam on these 10 questions, which I've already used for, right, explaining the subject for you? So that means you know what is the answer for this question. So when I conduct an exam, what will happen? What will be your performance? Yeah. What will be your performance?
Either fail or pass.
Why fail? I am saying that out of these
Oh,
100 questions only, I'm taking 10 questions, right? These
oh,
10,
okay,
100
okay,
questions I've
okay.
already trained you.
Yes.
So you would have close to 100% performance, isn't it?
Yes.
Because you know the answer already. But does that imply you already learned the subject? You also learning subject? Close to 100% marks is what you're going to get in the exam. But that does that mean you also have understood the subject here?
Not fully.
Not right, maybe, not maybe.
Yeah.
Because you know the question and the answer already. So you might have printed the answer as soon as you have seen the question without understanding the subject. You might have by hearted the question and answer pair. Right? So even in this case, you will get answer close to 100%, but without understanding the subject knowledge. Why the subject knowledge is important is because if you talk about external interview, this is something that we will not have control on, right? Now, in the external interview, you may get new questions from the same subject, but you may get new questions. Now, if you don't learn subject, will you be able to answer these new questions? Subject is important, right?
Yes.
So, students who give close to 100% performance in the internal evaluation, internal exam, may fail here, isn't it? So we have to evaluate the students internally first in such a way that they clear external exam as well. That means if I give a question which is not exposed to the student in the training, then how the student is performing, because that's what happens in the external interview, right? New questions will be given. To replicate this, what we do is to replicate this external condition, right? This external condition, what we do is we take this data, 100 questions, right? That we have, question bank that we have. We split this into 80, 20. Now what we do is we train students on these 80 questions, question and answers, of course. We do an internal evaluation here itself. On the same 80 questions, we will see how the student is performance. Okay, evaluate. Now I will know whether the student has actually listened, or maybe that the student is not even caring about this training. If the student is not focusing in the training, obviously the student will not clear the internal evaluation as well, right? So we will evaluate here. That will also tell us how good the student is training. But ultimately, remember, we want a student who can answer new questions from the same subject. So once we identify the best student here, we evaluate the best student on these questions, the 20 questions that we have taken aside. Now, these 20 questions are not used in training. So that means these are representing new questions scenario. Okay, unknown question scenario. Now, how does the student perform here? This is important for us. If the student performs on these 20 questions good, right? If the student is good, then yes, we can say the student is trained well on the subject, and we want this particular student to be sent to the external interview. Right? There may be students who really do good here, but they may fail here. That means the student has by-hearted the question answer pair rather than learning the subject. We cannot send such a student to external interview. Right? Internally, they may be very good. Maybe the best student is only getting 95%. And the student here may get 100%. But the 100% student may fail here in the test data case. Okay? But if the student is consistently getting similar result on trained dataset and test dataset, that gives us an evidence to understand that that particular student has learned the subject. This analogy is implemented for machine learning models. So the 10 students that we are talking about is like 10 different ML models that we train. Train on what? We have 100 questions with answers. These are 100 data points which are labeled questions, answers. Okay, labeled data. And then we use the historical data, that is these 100 data points, to train 10 different models. Okay, but again, we don't directly pass 100 records to train the model. We split this data into train and test. Okay, we do train and test split. And then we apply the same logic. First, we will train the model, evaluate the model on the training data set. We record the values that we are getting. And then we will try to measure it on test data also. And we need to see that there is consistency. Okay, we don't want overfit case. Overfit means on the training data set, the student gives very, very good results, right? But when that student is being evaluated on test data, new data, the student fails. That's called as overfitting. By hearting the question answer pair so that we get very, very perfect result. That's called as overfit. Underfit, of course, we don't want at all, because underfit means the student is not learning in this 80 questions itself. Underperformance. We don't need. What we need is the right fit. Right fit basically means the student who is consistently performing in all these data sets. Right? It's the same logic. Now, we talked about performance. I'm talking about how the student is performing here, and then we are trying to compare the performances, etc. But how do we actually measure the performance? Measuring is important, right? When I say measure, we need to have some quantified value which can explain how the performance of the student is on a given data, right? Isn't it? So, what is that measurement? That is also important for us to understand. I'm erasing here. The measure that we are talking about, right? The performance that we are talking about is measured using something called as metrics. In the student's example scenario, the student's exam scenario, the metric to measure the student's performance is their marks, which basically lies from 0 to 100, right? So we have a way to measure the performance, right? Those measures are called as metrics. So once again, when we talk about the machine learning models here, especially from predictive analytics perspective, we have regression techniques and classification techniques. In regression techniques, it's a numeric outcome, right? So that means what we do is we take all the input values. So here we have x1, x2, x3, x4, and let's say y. This is our historical data, right? Now, given this historical data, when we try and apply the data into this model, we will get some mathematical equation, right? So what we do is we substitute these values into this model and we do calculations. Now, the calculated values, right, we call them as fitted values, are nothing but your predicted values. So we already have actual values or observed values from the data, historical data case. And now we also have the estimated value, predicted value or fitted values. This is all on historical data, right? Let's say this is your test data set or trained data set, whatever that is, historical data. So what we do is we compare these two values, actual value and predicted value. Now in regression case, these are numeric values like student marks or sales numbers or age prediction, etc., depending on what we are trying to calculate. So here, let's say if the student is actually getting 85% marks given these fields, and our model, the best model, is saying that no student is getting 83%. Okay, this is the prediction. So that means we have gone wrong by 2%. How do I get that 2%? I can simply do the actual value minus predicted value. Mathematical computation. Subtraction is what I'm doing. This will tell me how wrong I was in predicting this student's marks, right? So this is the metric. Error is the metric that we will use for regression models. But again, remember, what I've given you an example for this error calculation is on one student, just one student. But the model that we are representing is being represented for the entire data. It may have 100 students or 1000 students or 1 lakh students or whatever that is, right? But a single equation is being represented for the entire table. So how was this model working on this entire table is something that we need to evaluate, not on one student. Like that, I have another student, another student, another student, right? So each student will have some error, right? That means in the table, I can imagine there is another column, right? Let me use a different color here. I will get another column, which basically is the subtraction of these two. Okay, this is nothing but error. So if I have 100 students, I'll have 100 errors. If I have 1000 students, I'll have 1000 students, 1000 errors, right? So on and so forth. So this is the error that we'll get. But remember, we need a representative value for this equation's performance on this particular data set. Okay, what I mean is if you are a student, you're not writing one exam, right? One subject exam. You will write multiple subjects, isn't it? But your academic performance is represented using a single number. In your resume also, you put that. Right? Now that is an aggregated value. So on the errors also, we need to get an aggregated value, which will be your metric to represent the performance of this equation on the data set. Right? Aggregated error. Now, when we say aggregated error, it is nothing but mean calculation, right? We say mean error. So we need average of these errors to be used for your metric. But unfortunately, or it's a behavior, it's not unfortunate, but it is the behavior of unbiased fair model that it balances all these errors. That means the average error for any balanced model, a fair model, will always be equal to 0. Okay, this is one of the property. Okay, so we will not say that error is 0. Okay, because is this error 0? No, right? We get 2 units. But the aggregated response basically shows that this model is perfectly fitting the data, which means error is 0, right? Which is not true. So what we do is to remove these negative errors, positive errors, right? Because of which we get 0 here. We only capture the magnitude of errors by taking square of those errors. Okay, we take squared values of errors. Error squared will be taken. That way, if I have any negative values, will be removed. And we will only capture the magnitude, not the direction. Okay, average is nothing but sum of the errors by total, right? But some of the errors will become 0 because of negative values. So here we are removing that and then calculate the mean of squared errors. Okay, here we will get mean squared errors. But units also get squared. It doesn't make any sense. So what we do? Finally, after calculating it, we take root mean square error. Now, this is the metric which needs to be used for evaluating the regression model. Okay, RMSE. So here we will talk about metrics. Depending on what kind of output the model is giving, we will be implementing that specific method and it gives us the specific metric. Okay, for regression techniques, the metrics that we use is RMSE, which is basically nothing but root mean square error. But there are variations of error calculations, like we also use MAPE, mean absolute percentage error, which is again a different way to represent the error, aggregated error, but that comes in a percentage form. Okay, we also use MAPE. It's nothing but mean absolute percentage error. Okay. So this is for regression cases. Of course, model evaluation always happens by data partitioning. We split the data into train, test. Okay. We also have something called as validation. This is used for hyperparameter tuning, experimenting the model. I'll talk about that also. But for now, train and test. Okay. And the test metrics, right? The metrics that we get here are called as generalization metrics. Because test data is something which resembles new data, unknown data. So if your model is performing well on new data, that gives us information or confidence to say that, yeah, this model will work on external interview case also, right? Any new data that is coming from the same subject, the model might work well. Okay, that is what your generalization metrics means. And what we do is we compare the performances of these models, right, using the metrics that we are calculating here. Okay, and what we do is compare the metrics for train, test, samples. Here we get overfit case, or I should say underfit to start with, or overfit, let's say. Then we have right fit, and then we have underfit case. I'll write like this, okay? Underfit. Here we'll say right fit, and here we will say overfit. So overfit is when the model's performance, right? Error, if I talk about error is less on training data set, error is more on the test data set. But if I talk about performance, then I'll say model is performing very well, right? Good performance on train, bad performance on test data. This is overfitting. Identically good and identical or similar, I should say, performances on both train and test. This is what we need, the right fit. And underfit basically means bad performance on train itself. Okay. This is like students applying for civils, for example, right? Any competitive exams. Generally, what happens? Students get trained, they will write prelims, right? And if the student performs well in the preliminary exams, only then they will get qualified to the final exam. Isn't it? If the student does not perform in the prelims itself, then there's no point, isn't it? They're completely disqualified. They will not be passed to the next main exams, right? So that is underfit case. There will be few students who perform really well in the prelims, and in the main exam they will fail. That is called as overfit case, because the students may have by-hearted shortcuts to remember the questions, right? Questions and answers. So they get good marks in the prelims, because prelims are generally done on historical exams, right? Those questions only. So when we talk about main exam, the student may not perform well because the questions might completely change, or maybe the logic of the questions might change, right? The pattern might be changed. So student may not learn the subject. In that case, student not performs good in the finals. Obviously, they will also not be finally given the opportunity, right? But the best student would be those students who perform consistently well both on the prelims and in the finals. That is what we require, right? Right fit. So this is how the comparison happens. But till now, I'm talking only about what regression case, where your model is actually giving numeric outcome, right? Numeric values. Then we can calculate error. How? We simply subtract actual value minus predicted value. I've given the example of 85% and 83%, right? But what if non-numeric values are there to be predicted? That means we are talking about the models which are trying to predict non-numeric values, classification models. I'm talking about student pass or fail. Now, in this case, non-numeric case, I cannot say, sorry, actual value minus predicted value. It doesn't make any sense, right? If I try to subtract pass minus pass or pass minus fail. Non-numeric data, isn't it? So we cannot use the simple mathematical error calculation here. That's not possible. So rather what we do in this case is we get the predicted value, right? When we apply the model, we get predicted result. We take this predicted value and then compare this with the actual value. We already have actual value, right? We compare the predicted value with actual value. Now, when I compare, remember it is a comparative operator. It's a comparative operator. So in the comparative operator, I will always get the output in true or false case. Okay, we'll always get true or false as an output for comparison operators. That means if I have predicted value as pass and if the student actually passes, then the comparison is true, right? But if the predicted value is pass, but the actual student, I mean, in actual, the student failed, then this is a false case. Likewise, we may predict the student is failed and the student might actually pass. So I'll get false output here. And I may have student fail and in actual, the student might have actually failed. So this is giving us true result. So this way we compare. And what we need is true predictions because that is where your model is actually performing like what we expect. Right? It is giving us the expected result. So all the fail cases means the model did not perform well. So we use this comparison technique and we collect all the true values from total. This gives us accuracy. So we use accuracy metrics as well, which is nothing but sum of true values by total values. Okay, sum of true values by total values. If I say 1 minus accuracy, that gives us overall error. That means sum of false cases. So there are many other metrics that we will be actually looking at. But at a high level, these are the metrics that we do compare for doing model evaluation. Okay, so this is the overview of CRISP MLQ. I'm just talking about high level things for today, first class. And as we unfold things tomorrow, again, we'll talk about deployment strategy. We'll talk about monitoring and maintenance strategy. Post that, I will try and revise these algorithms, quickly revise these individual algorithms that we have recorded here. All right. Any questions in today's session? It's already 8:30. Yeah. Any questions, friends?
No, sir.
Okay. All right. Okay, if no questions, then we'll wind up the session. We'll connect tomorrow. Okay. All right. Thank you, friends. We'll see you tomorrow.